Now?
Yes, now yes. Well, welcome to our session for today. First talk is by Giulia. Please, Giulia, go ahead.
Just a moment. Okay. So, good afternoon to everybody. I'm very pleased to be here today with all of you. First of all, I would like to thank the organizers for having built up this amazing workshop. And I would like also to thank them a lot for having given me this excellent opportunity to share my work with all of you. My talk will be about very interesting phenomena occurring in liquids at finite temperature, emerging from a weakly interacting Bose-Bose mixture in one-dimensional, in one spatial dimension. And I would like also to give you some interesting perspective about the impurity problem. First of all, I would like to thank a lot my very nice collaborators, so Grigori Astrakarczyk and Pietro Massignan, working in my group at Universitat Politecnica da Catalunya in Barcelona. And if you are interested, you can find further details in our published paper of 2021. But I would like to start by convincing you that very interesting and different kinds of physics occurs in bosonic binary atomic mixtures. So let us consider an atomic ensemble of two different bosonic atoms here reported by the red and the blue atom. And if we consider, for example, the case of for which the densities of the two atomic species are of the same order, which means that they can be equal, but they can be also different. The most important thing is that more or less they are of the same order. Then very interesting phenomena, and also very recently predicted, occur. And these two phenomena are liquid droplets and mixed bubble, and their existence can be explained with beyond mean field effects. And I would like also to remind you that usually beyond mean field effects are neglected in ultra-cold single component Bose gas, and now we need to take into account them in order to explain the merging of droplets and bubbles. Well, droplets are a new state of liquid matter, and we need an attractive interaction between the two different bosonic atoms. So the attractive interspecies interaction. And they have been predicted in 2015 by Dima Petrov, and they have been also observed firstly at ICFO by the group of Letizia Taruel in Barcelona, and secondly also at Lens in Florence in 2018. Then, if we consider instead a repulsive interspecies interaction, then one can observe the emergence of mixed bubble, which means that we have a bubble of the mixture immersed in the single component gas. And this very nice prediction is very recent, is of this year, later by Pascal Naidon and Dima Petrov. But if we consider instead the case of highly unbalanced mixture, which means that the density of one species, which we recall the impurity, is much smaller than the density of the other species, which we recall the bath, then one can investigate other phenomena regarding the so-called dress impurity or Polaron problem. And the idea of the formation of the Polaron is also very nicely depicted in the book of Matuk, for which we can consider a real horse, so a galloping horse in a western, and this horse is our moving impurity through the bath. So at a certain moment, this horse is surrounded or dressed or screened, if we want, by the dust cloud. And this cloud is the analogous of the cloud of the excitation of the bath. So at a certain moment, we cannot see anymore the real horse, which was, let's say, the bare impurity. And we need to consider instead the combination between the horse and the dust cloud. That is to say, we need to consider the combination between the bare impurity and the cloud of the excitations in the bath. And this combination forms a new quasi-particle called Polaron. And this problem actually is very interesting because actually, thanks to the presence of the cloud of the excitation, the properties of the Polaron actually are very different from the properties of the corresponding bare impurity. So we can discuss about an effective mass or also an effective interaction for the Polaron. And in particular, if we consider that the bath is composed by bosonic atoms, one can discuss the problem of the Bose Polaron. And finally, the Bose Polaron has been observed both at Gila and in Aarhus in 2016. And in particular, its energy has been measured both for the attractive and repulsive impurity bath interaction. But now let's jump, let's say, to the main topic of my talk, which is ultra-cold atomic liquids. And I would like to remind you what is the difference between a liquid and a gas in classical physics. So a liquid such as water is usually dense. It is self-bound in the sense that it does not require any external container. And it is self-bound because of the perfect balance between the attractive and the repulsive forces, thanks to which there is the arising of an equilibrium density in liquids, which can be calculated with the zero pressure condition or with, in a completely equivalent way, the minimum of the free energy per particle. And in particular, in the liquid, the pressure can be also positive and negative. On the other hand, in a usual classical gas, the system is very dilute. It is not self-bound, so it always requires an external container, and its pressure is always positive. Then, by increasing the temperature of the liquid, one can observe the phase transition to the gas, which is provided by the interplay between the thermal kinetic energy and the attractive forces, which make the liquid really self-bound. And novel quantum liquids have been recently discovered in ultra-cold atomic gases, and the original configuration was a three-dimensional mixture composed by two bosonic gases at zero temperature, and the requirements were an intra-species repulsion, so atoms of the same species are actually repulsive, and atoms of different species are actually attractive. And differently from water, these exotic ultra-cold atomic liquids are really ultra-dilute and also ultra-cold much more than water. And these have been predicted by Dima Petrov in 2015. And the emergence of these novel ultra-cold liquids can be explained thanks to beyond mean field effect. So in the energy functional, we need to consider not only the mean field contribution, but also the beyond mean field contribution, by considering also that these two terms exhibit an opposite sign. And by tuning the interatomic interaction, one can make the mean field contribution very small, such that in this very special situation, the beyond mean field energy contribution now cannot be neglected anymore, as it occurs in a single component Bose gas, and needs to be taken into account. And in particular, the interplay between this mean field and beyond mean field energy contribution is very important, because if one considers the energy per particle as a function of density, one can observe the emergence of a minimum at a negative energy and corresponding to the zero pressure condition, from which we can calculate the equilibrium density. And the presence of this equilibrium density actually characterizes the existence of a liquid and makes really the liquid different from the gas. So this means that this novel ultra-cold liquid droplets in mixture make for the first time beyond mean field physics really important, differently from a single component gases. And finally, these liquids, actually droplets, that is to say small parts of these liquids, have been observed in 2018 at ICFO, but also at LENS. And their observation was really based by turning off the external trap and by observing the time evolution of the gas and the liquid. So for example, if one considers the first row, we expect that by turning off the external container, the gas will expand. And if we consider the second row, which is instead the liquid, since the liquid is self-bound, differently from the gas, it will remain there stable as a function of time. And thanks to this different behavior as a function of the time after the turning off of the laser trap, the liquid was really identified and distinguished from the gas phase. But there were, let's say, some experimental open problems in these ultra-cold droplet experiments. The first one was the very short experimental lifetime, and which made basically impossible any further investigation, especially regarding the dynamics or collective oscillation occurring in these ultra-cold liquid droplets. And finally, also the fact that actually the temperature in this liquid cannot be measured, especially with the usual and standard time of flight expansion technique, which is applied in gases. And this method is based on turning off the external trap of the gas, measuring the final atomic velocity, and reconstructing this way the original kinetic energy and so the temperature of the atomic ensemble. And obviously, this time of flight expansion cannot be applied to liquids because they are self-bound and they don't expand. So we need novel experimental techniques in order to measure the temperature in liquids. We don't know how these liquids also behave with temperature. And why we are interested in studying ultra-cold liquids in one spatial dimensionality? Because at the end, they are much more stable. In fact, in 1D, 3 body losses are highly reduced because it's very difficult to get a collision between 3 atoms. And also in 1D, beyond mean field effects are strongly enhanced. So in particular, both quantum but also thermal fluctuation are highly enhanced. And since quantum fluctuation are responsible for the stability of these liquids, especially at 0 temperature, this is really promising for saying that in 1D, actually, these novel phenomena are much more stable. And these actually have been also predicted in 2016 by Dima Petrov and Grigory Astrakarchik at 0 temperature. So what we have investigated, it's a weakly interacting liquid in one-dimensional Bose-Bose mixture at low temperature. And our Hamiltonian is this one. So we consider the kinetic contribution for both species, the interaction between the 2 components. So we have this coupling constant G, which is the intra-species interaction, and this coupling constant is positive. So we have an intra-species repulsive interaction, and we have also chosen the same coupling constant for the 2 atomic species. And then we consider an attractive interaction between different components. And finally, we have also considered the balance mixture. So we have the same number of atoms for both species in the mixture. So at 0 temperature, everything was more or less known in the weakly interacting regime by applying the Bogoliubov theory. which holds only in the high density regime, where the gas parameter is very large. And so we can write down this energy density depending not only on the total density n, but also on the two phononic sound velocities, which are itself a function of the two coupling constant G and G12. And these phononic sound velocities actually provide the leading contribution, so the phononic linear term in the two Bogoliubov spectra. So we have two different branches of the Bogoliubov spectra, as you can see here. And so yes.
Dima.
Yes. Is there
Hi. What happens if G12 is greater than G?
If G12 is greater than G.
I mean the absolute value, right? So you have sound. So sound
Yes.
cannot propagate in one of the modes. Is a kind of instability then?
Yes, because okay, I will skip it just some slides just to. Yes, okay, because actually in our theory we have considered the ratio G12 always smaller than 1, so G12 always smaller than G, because these are actually the condition for which we can form a liquid. In the different case for which G12 is instead greater than G, we have firstly an instability, and then by increasing further G12, we will have the formation of a soliton. So it is a regime beyond our.
Can I comment on that? I think that's the situation when G1D is larger is always unstable. So if in the present case there is attraction, so essentially it collapses to sort of a soliton. Instead, in the case when everything is repulsive, then G1D larger than G is also unstable, but for repulsive case due to the phase separation.
Yeah, I agree.
Yeah, please go on. Sorry.
I will come back. Okay, so we have considered a regime at low temperature, and also for weak interaction, where the temperature is much smaller than the quantum degeneracy temperature, depending on the square of the density. And in this description, we can still apply the Bogoliubov theory, and the idea is to model our weakly interacting liquid in terms of the non-interacting bosonic quasi-particle. So in terms of the ideal Bose gas of its excitation. So we write down the free energy of an ideal Bose gas, but since now we consider the free energy of the quasi-particles, we set equal to 0, the chemical potential appear in the free energy. And so we can write down this thermal free energy density where we have the sum over both Bogoliubov spectra, and also it is a function of the two Bogoliubov dispersion. And so at the end, it is a function of the two phononic sound velocities. So from the free energy, basically, we can calculate any thermodynamic quantity of interest, such as, for example, the chemical potential, the pressure, the inverse isothermal compressibility, and also many other, and you can find their detailed derivation in our paper. But in particular, we focus now on the inverse isothermal compressibility, because if it is equal to 0, one can calculate the spinodal density, which actually sets the stability condition for the liquid. In particular, if the density is greater than the spinodal density, that is to say that the inverse isothermal compressibility is positive, then the liquid is stable, which means basically that if we compress the liquid, the reaction of the liquid is a positive pressure, so the compressibility is positive and it is fine. In the other case, if the density is smaller than the spinodal density, then the inverse isothermal compressibility is negative, so the liquid is unstable and it breaks down into small pieces, which are droplets. So basically, here we are investigating the liquid gas phase transition at finite temperature. So we are considering a tube, an infinite tube of a liquid at 0 temperature, and we start to increase its temperature and to see what happens. So here we have the free energy per particle as a function of the density. And we have reported only the stable regime of the liquid. So the density is always greater than the spinodal point, for which the compressibility is always greater than 0. Let's start from 0 temperature, so the black solid line, and we observe that this free energy per particle exhibit a minimum corresponding to the equilibrium density of the liquid. So since we have a minimum, we can identify this state as a liquid. And actually, if we increase the temperature until to 0.3, so the red solid line for this 0.75 of the ratio of the two coupling constant, we still have a liquid because we still have this minimum in the free energy per particle. But again, if we increase the temperature by keeping fixed the ratio of the two coupling constant, we don't observe anymore the minimum in the free energy per particle, and so we have the phase transition to a gas phase, where basically the free energy per particle is just a monotonic increasing function with the density, and it is reported here with dotted lines. On the other hand, if for the same values of temperature, we increase instead the ratio of the two coupling constant, we get again a liquid because we observe again the emergence of the minimum and so of the equilibrium density. So this means basically that if we increase the temperature, we also observe that the equilibrium density approaches the value of the spinodal density. And we can investigate the liquid gas phase transition at a critical temperature, which can be calculated from the condition for which the two equilibrium and spinodal densities are equal. And actually, the same information is reported in our phase diagram here, where again, we have the inverse density as a function of the ratio of the two coupling constant to G12 over G. All the dashed line are the equilibrium density solution for the liquid for different values of the temperature, while the solid lines are the spinodal densities. And we observe actually that by increasing the temperature, the equilibrium densities start to cross the solid lines, so the spinodal densities. And when there is this crossing, we can calculate the critical temperature corresponding to the liquid gas phase transition. And actually, this phase transition is driven by a thermal mechanism called the dynamical instability. And from this phase diagram, we also observe that the thermal effects are much more evident for smaller ratios of G12 over G. And this ratio actually provides a picture of, let's say, a measure of the attractive forces which make actually the liquid self-bound. So if the liquid is characterized by a small attraction, is much more sensitive to the effects of temperature, and so the phase transition will occur much more easily. And in the inset, there is the same phase diagram, but for a given value of temperature. So basically, where we have the equilibrium density solution corresponding to the dashed line, we have the liquid, and the pressure changes sign around this line, where instead we don't have anymore this equilibrium density solution, we have the gas corresponding to the right side sorry, to the left side of this phase diagram. On the other hand, above the solid lines corresponding to the spinodal density solution, the isothermal compressibility is always negative, both for the liquid and both for the gas. So in the case of the liquid just breaks down into droplets. In the case of the gas just collapses by forming the so-called Bose supernova. And the border between the gas and the liquid is really provided by the condition for which the two equilibrium and spinodal densities are equal. But actually, there is also another thermal mechanism driving the liquid-gas phase transition, which is the evaporation, which, differently from the dynamical instability that I showed you before, actually involves just the surface of the liquid. So the idea is that the liquid just loses some atoms from its surface, and this occurs when the thermal energy becomes roughly equal to the chemical potential at 0 temperature, because actually the chemical potential provides the amount of energy we need in order to add one particle to the system, which in the same perspective is also the energy we need in order to, it's the energy that the liquid loses in order to evaporate one atom, let's say. So in this plot, we have reported the critical temperature as a function of the ratio of the two coupling constant G12 over G for both the dynamical instability and the evaporation mechanism. The black solid line is the calculation for the dynamical instability from the condition for which equilibrium and spinodal densities are equal, calculated with the full Bogoliubov theory, so with the full Bogoliubov spectrum. While the dashed line is instead the same information, but by taking into account only the phononic contribution into the two Bogoliubov spectra. And
what's on the axis? What's on the axis in this plot?
The axis, okay. The
temperature, okay. I see.
Yeah, the critical temperature as a function of the ratio of the two coupling constant.
Okay.
So it's the critical temperature as a function of the attraction in the liquid, let's say. And we observe a deviation from between the solid line and the dashed line, so between the full Bogoliubov theory and between the phononic theory, let's say, especially at large values of the ratio of the two coupling constant. So this means actually that our full Bogoliubov theory works a little bit more better than the corresponding phononic theory. On the other hand, we have with dot dashed line the critical temperature associated to the evaporation and calculated from this condition between the thermal energy and the chemical potential. If we consider the smaller values for the ratio G12 over G, the critical temperature is smaller for the dynamical instability, while on the other hand, at larger values of G12 over G, the smallest value of critical temperature is the one of the evaporation. So this means that at small values of G12 over G, which means small attraction, the liquid prefer to transform into the gas phase through the mechanism of the dynamical instability involving the whole volume of the liquid. On the other hand, at larger attraction, the liquid is much more self-bound, so the ratio of G12 over G is much larger, and the liquid, since it is much more self-bound, it prefers to evaporate, so to just lose some atoms from its surface.
Excuse me.
Yes.
I didn't quite get what is the order of this phase transition? Is it the first order transition or a second order transition?
This is the big question in our work, because Okay, actually, okay, I'm not reported here the corresponding result in these slides, but it is reporting in our paper. We have also calculated the specific heat as a function of temperature for this system, and we don't observe any peak in the specific heat. So we
Yeah,
are
that's quite natural within your approximation. So I would think, actually, this is logically within your approximation. It is logically impossible to have a second order phase transition between the liquid and the gas, and the reason being, if you have a finite number of particles inside the finite volume, and you look at your system at phase transition, there has to be liquid vapor separation. Otherwise it's just logically impossible to have a liquid with the right, which would minimize the energy, right? Achieve the right density. So in fixed volume with a fixed number of particles, in order to achieve the liquid density, you'll have to go for the phase separation, liquid versus vapor. And that means that you have first order phase transition by definition of the first order phase transition. So that's the first observation. The second observation is, if it is a first order phase transition, then there is a slight problem in the one-dimensional case, which is, as you probably know, the proliferation of the phase boundaries. The problem is, and it is written in the Landau-Lifshitz textbook, the problem is that if you create a number of phase boundaries between liquid and vapor, you pay the surface tension energy for that, sure, and that is proportional to the number of phase boundaries, but you also increase the entropy in your system, which is proportional to n log n, and n log n wins over the energy cost. Therefore, if you try to cook up a system with the first order phase transition in one dimension, that won't work because the phase boundaries will proliferate and your system will homogenize. The phase separation is impossible in one dimension at any finite temperature. So there is a bit of a problem with the which is not, of course, captured within your approximation, because you do not consider topological defects inside your model. You only consider vibrations, but that raises a serious question as to the experimental manifestations of your phase transition. So can you comment on that?
Okay, actually, okay, we know that in 1D at finite temperature phase transitions are forbidden, but it is a still debate point if this is true even in the case of mixtures. And in order to test if the transition was a second order phase transition, again, we have calculated the specific heat and we don't observe any sign of per second. Yes.
I'm not surprised by this, but then this has to be a first order phase transition, which is not possible in 1D anyway. So that raises the question about the experimental manifestation. The physics which you described here certainly exists, but the serious question is, how does it manifest itself in an actual, this Gedanken experiment? It is not phase separation. Phase separation is not possible because of the proliferation of phase boundaries. So what is going to happen in that phase transition point is a question to ask, if anything.
Yeah, and then actually in order to test if it can be considered the first order phase transition, we have investigated if phase coexistence between the liquid and the gas is possible in our system, and actually it does not, because if we look at, for example, our phase diagram, actually we need to fix the ratio of the coupling constant. So we are fixing basically also the phase, because if you fix this ratio, you will have or the liquid or the gas, but not both. So actually, this is exactly a really open and pretty debated point of
But
our work.
it's hugely confusing. Yeah, it's hugely confusing because if there is no phase kink, there's no phase kink existence even in your approximation, which is a bit of a surprise. Yeah, what then happens? I mean, your liquid phase wants to maintain a certain density, which which you cannot ensure if you have a fixed volume and a fixed number of particles. So what happens in that system then? You can't have your density because the density is imposed from the outside, and you can have phase separation. So what do you have then? So that's a serious question. That's about experimental manifestations of your physics. What do you expect to observe in that situation?
Okay, so you're saying that since we have the liquid, we need to fix its equilibrium density, right?
Yeah.
Okay. Yeah, I mean, this is an excellent point, because if you increase the temperature in order to get to still have the liquid, even the equilibrium density will change with temperature. So not only with the interactions, but also with temperature.
Yeah, so that's a curious, that's an interesting question, because that's about the observed physics, observational reality, right? Okay, yeah, I understand the status of this problem.
Okay.
Okay, thank you.
You're welcome. Okay, just to summarize, we have investigated a weakly interacting liquid in a one-dimensional Bose-Bose mixer at a very low temperature. And we have also calculated all the main thermodynamic quantities of these ultracold liquids for the first time, like the sound velocity, the chemical potential, the specific heat, and also both inter and intra-species stance contact per meter. And you can find them in our manuscript. We believe that our work is pretty interesting, not only for the first observation of this liquid gas transition driven by temperature, but also because our phase diagram is suggesting a new way of realizing the liquid just by cooling the gas. And then in 1D, liquids are much more stable because the three body losses are strongly reduced. And this is really important because, differently from what happens in the first experiments in three spatial dimensionality, these three body losses actually enter the possible identification of the evaporation mechanism, in the sense that in 1D, for the first time, it would be really possible to identify the evaporation and the three body losses. And finally, we are also suggesting novel methods of measuring the temperature in liquids based, for example, on the dependence of the critical temperature on the interactions, which is an highly controllable parameters with Fano-Feshbach resonances in the experiments. And also we are suggesting that we can estimate the temperature in liquids by measuring the thermodynamic quantities that we have calculated, which are obviously a function of the temperature. And just also to give you other perspectives of our work can be also interesting for the Bose Polaron problem at finite temperature. So the first idea would be to add an impurity to the liquid. And this can be very interesting, not only for the Bose Polaron community, but also for the ultracold liquid community, because the impurity can be used as a probe in order to test the properties of the liquid, whose knowledge is very limited, especially at finite temperature. And this actually has been also suggested in another kind of ultracold liquid with bipolar interactions. And we are suggesting basically we are suggesting the same thing, but in our isotropic liquids with contact interactions. And also it may be interesting to study the Bose Polaron at finite temperature immersed in a liquid, because since we are changing the bath, so not only the single component gas, but now the liquid, we are expecting also that the Polaron properties will change. And then I have discussed how we can study the liquid to gas phase transition by increasing the temperature, but actually we expect that a liquid to gas transition is also possible by just reducing the density of one atomic species. And ideally, if one reaches the highly unbalanced limit of the mixture, one can achieve the limit of the Bose Polaron at finite temperature, which is actually a very hot topic right now, not only because the first two experiments in 2016 were performed at finite temperature, but also because there are plenty of very interesting theoretical works about this topic. Some of them are also from my research group, and I would like to outline just this work of this year, which is very recent, and it is a theoretical investigation of the Bose Polaron problem at finite temperature with Monte Carlo method. And this limit between, and this transition from, let's say, the liquid and the Bose Polaron also suggests the building up of an unified description of a bosonic binary mixture, where the liquid and the Polaron are very interesting limiting regimes, and they can be also used as important benchmarks to test this unified theory at finite temperature of bosonic mixture. So thank you very much for your attention, and I'm looking forward to your questions. Thank you.
I presume if in the limit of G going to infinity, and you can have an integrable situation, right? So you can have some exactly solvable
Yes.
possibility. Did you explore this possibility?
So you are saying
Or
these
are there plans to explore it?
This intraspecies interaction G is infinite, right?
No. The yes, intra.
Intra, so the coupling constant G. Okay, in this case, this ratio is 0, and actually it's very far from our regime, because the liquid can be formed only if this ratio is very close to 1, and in particular we have considered heat larger than 0.7 because there is an excellent agreement with Monte Carlo at 0 temperature with the Bogoliubov theory. So no, we don't know.
So there is no interesting reason.
Yes, but it's not clear how to solve it. So you want kind of intraspecies infinite, and you play with G1, 2, but then it's exactly solvable, and there is no bound state. So there is not more than one diamond. It's a young Gagan mode, right?
Yeah.
So there are no tetramers and things like this. So there is no liquid. And then you have to play with some finite G11, G2, G12, but this is in the strongly interacting regime.
Because somehow this is equivalent to having fermions with some attraction, which is young, and there is no liquid there.
Yeah, after question of Vadim, kind of, I should speak milder, but just for those who, okay, I'll put it in a very imprecise way. If somebody wanna quit this room with a single line message from the study of your particular system, which message you would like to deliver? There are many 1D systems, especially when you use components, interactions, they are all different. So what is so particular about what you did, what you want to kind of give as a memory of your talk for people who are not in this field? What do they learn?
Okay, our work is one of the few works about the finite temperature behavior in ultracold liquids. There are also other works, but we also believe that our work is more completed because differently from the other works, we have also investigated the evaporation phenomenon, which was not present in the other two works. And we have also provided a full investigation of the thermodynamic properties of these novel liquids. And finally, we also think that I mean, the liquid occurs in the balanced mixture, in a balanced bosonic mixture. So it can be also the starting point for studying the Polaron problem by reducing the density concentration of one species. And also, we have also provided important experimental insight, like new methods for measuring the temperature. So not only the theoretical prediction of phenomena, but also how to measure the temperature in liquids, which is missing, let's say.
Thank you.
Thank you.
Any other question from online people? Okay. Dima.
Hi, Giulia.
Hi,
I have a question. So about this, okay, evaporate. So I understand your work is like this. So you start with a, let's say at zero temperature, you start with a droplet of n particles, and up and down in a box of certain size. And then you start to heat it, right, with finite temperature. So what I understand is that it will lose particles, right? So they will go to the gas phase. So it will be flying around in this volume, and the droplet will shrink because it will lose particles, right? So this is what I understand as evaporation. Is this correct?
Yes, but we expect that this occurs for larger values of G12 over G.
Large means closer to the, let's say, collapse line. That's right.
It's here, yes.
And the other regime, what in this picture that I have just, that you start with the other regime. So you fix G12 in another regime. So deeper, let's say, strong interactions, right? In the box, I start with a droplet. I start to heat it. What happens?
No, okay, let's do a concrete example. So we fix a G12 over G to 0.75. So since the critical temperature, the smallest value is the one of the dynamical instability, we expect that by increasing the temperature, the liquid basically disappears completely at a certain moment, and it transforms in this way to the gas phase. So it's a volume.
So, okay, if I just look at the droplet like a condensate wave function, right? What will happen? So it will not shrink with the fixed density, but it will decrease the density and will increase its size. How will this happen?
Okay, let's see this phase diagram. So we increase the temperature. So this ratio increases. So this means that actually the density increases.
Increases?
Yes, but sorry.
This is for fixed chemical potential there, or for fixed number of particles? It may not be applicable directly to what I'm saying. I'm just trying to understand more or less the experimental kind of canonical picture.
Okay. Sorry. What happened? Okay, I think that there is a problem. Yes. Okay. Here we have the free energy here. So yes, we observe that the equilibrium density by increasing the temperature actually gets smaller.
I see.
So it's less, yes. It's
So
more
you lose particles not by changing the size of the droplet, but by changing its the height. Okay, I see. And this is the different regime that you're calling not evaporation but something else.
Yes, it's the dynamical instability. This plot is referred to the dynamical instability as our phase diagram. Yes.
Okay. Okay, thanks.
Thank you. You're welcome.
Misha.
Так. Anybody wants to ask something? Так. We thank Giulia. We stop recording.
Thank you.